So this lesson is about what we call implicit differentiation. Again, differentiation or differentiate just means take the derivative of. So this is just a new type of taking derivatives. Differentiation. Very good. So before we can understand what implicit differentiation is, we need to understand what this implicit word comes from. So to talk about what implicit means, we're actually going to start by talking about what explicit means. And that is, well, the word explicit just means very direct or something, right? Um, well, explicitly, a function is defined when it's just y equals something. When I tell you explicitly what y has to be, right? This explains what y is. So something like x squared plus 2. That is an explicit function, right? An explicit equation. Well, the other side of that is something implicit, where it implies what the function y must be, or what our variable y must be. So this would be something like y squared is equal to, sorry, instead of 1, I wanted x. Now, this relationship, I don't immediately get to plug in a number for x and immediately know what the output is. So for instance, if I want to find the x and y value when my x is 1, I don't immediately know what my y values are, right? This doesn't just literally tell me what that y value is. So instead, we have to simplify, we have to solve for y. And it turns out this is y equals plus or minus the square root of 1, which is plus or minus 1. So this is something really, really worth emphasizing, and this is kind of the whole point of this section, is we can have implicit relationships, implicit functions, per se, because y itself is not a function. However, y does correspond to two functions. In this case, two functions, that is, the positive square root of x and the negative square root of x, right? Each one of these individually is a perfectly valid function. However, this relationship is not a function. Why? Because for an x value of 1, I have negative 1 and positive 1 as valid coordinates. However, if we try and graph this implicit relationship, right, the graph actually looks something like this. I didn't draw it perfectly, maybe arguably I didn't even draw it very well, but that is the graph of this relationship. If we graph every single coordinate here, this is what we get. And it turns out this is something meaningful, right? It looks just like a normal parabola if we like flipped it somehow. So it turns out that these implicit functions that are sitting inside of these relationships um, are meaningful to us. So this is when I tell you the value for y implicitly, and this is when I tell you the value for y implicitly, as opposed to when I tell you the value for y explicitly, right? Okay. And again, this relationship here is not a function. However, it implies two functions from that. Now, the thing is, if I'm able to look at this graph, then, and it kind of makes sense to me, then hopefully I can figure out some way of taking a derivative along that graph. And it turns out that is exactly where implicit differentiation comes into play. So, the trick here is if I want to take the derivative of this expression, that like literally this one that I already have written down, I need to recognize, right, that y is supposed to be a function of x. So we write y, but we also write that like f of x, right? So another way to write this relationship is some function squared is equal to x. Well, now when I take this derivative, it might be a little bit more clear to us that we need to use the chain rule. So using the chain rule, right, we identify that this is the function f squared. So the outside part is, squaring, so the 2 comes out front, subtract 1 from the power. This is f of x. But then the chain rule also says we multiply by the derivative of the inside. Well, what's the derivative of f? I don't know any better name to call it than just f prime, right? So that's for the left-hand side of my equation. Now, for the right-hand side, I see x, right? This isn't a function. This isn't anything in terms of y that I need to look at special. This is just x, right? Something in terms of x. So that derivative happens like normal. What is the slope of the line y equals x? Just 1, right? What is the coefficient in front of here? 1, right? So I did this implicit differentiation, and now I have this new expression. So I have 2 times our function times f prime is equal to 1. And what we want to do is actually solve for my derivative and write this as 1 over 2 times the output of whatever my function is. So now what we just did was a really clever way of ignoring the fact that I have 2 different functions that I'm looking at, right? In reality, these are 2 separate functions that I would want to take the derivative of. However, that's the theory of it if we didn't know better. However, with implicit differentiation, we don't have to do that. If we just acknowledge y is some function, then I can still make this relationship with the derivative. Very good. And with implicit differentiation, what's actually really, really common is we don't always go back and forth between y and f of x, right? Because writing f parentheses x close parentheses is a whole lot more work than just writing the variable y. So oftentimes we just write, instead of f of x, we just write y. And instead of f prime, we write, or f prime of x, we just write y prime. So really, I'm going to redo this question with the notation that we're going to be using when we take or do our implicit differentiation, right? I'm going to leave it with y and say, okay, well that's the chain rule because y is always a function for us unless the question says something weird and different. So I have a power rule, or sorry, we have a chain rule and the power rule on the outside, so the 2 comes out front, and then derivative of the inside. Derivative of y is y prime. Derivative of x is 1. So because I want to know the derivative that I'm solving for, then I'll write this as 1 over 2y, right? And again, this is exactly the same thing. It's just whether I'm writing this as the function f of x or the variable used to denote the function y. Okay, so this is very good and very useful. So a thing that might be asked is something like find all tangent lines for the x value. X is equal to 2. Actually, yeah. Yeah, that's fine. No. We'll do x is equal to 4, just to make things a little bit cleaner. Okay. So this is different than the kind of questions that we'd asked previously, because when we have an actual function, one x value, right, I'll write this down. Function, one x value, one y value. Relation just gives us one x value that may correspond to many y values, right? And so that's the issue here. Because we're sitting inside of implicit differentiation, we must not be able to write things as a nice and clean function. So because we just have a relation, instead of saying find the tangent line, if this was a normal, if this was a function, instead, because we have a relation, because we have a relation with many y values, so therefore many, not may, coordinates that look like 1, comma, something, right? Now we have all tangent lines that we need to find. There's not just one tangent line for a given x value because there's multiple coordinates that we need to consider. Okay, so again, the question that we care about here is find all tangent lines for x is equal to 1. So the first step I would say is find all y values where x is equal to 1. So if we have y squared is equal to x, then this is y squared is equal to 1, which we already figured out. That means y is plus or minus the square root of 1. Well, the square root of 1 is just 1, so this is plus or minus 1. So the two coordinates that we're going to consider are 1 and negative 1, as well as 1, comma 1, right? Plus 1 and minus 1 as our two y values. Great. So now we figured out that y prime is equal to 1 over 2y. So for this coordinate, m is equal to 1 over 2 times negative 1, aka negative 1 half. Now for this coordinate, m is 1 over 2 times positive 1, so this should be positive 1 half. Well, does this make sense with the graph that I drew? Well, if this is 1, this is 1, and this is negative 1, then at 1 comma 1, we should have a slope of positive 1 half. Well, sure, that looks good enough, right? 1 half x plus something. And then over here, right, the graph is going down, so a slope of negative 1 half, sure enough, should make sense to us, right? However, this said the tangent line, not just the derivative at that point. So really we want a y equals mx plus b situation, right? So we figured out the slope. So we have y, oh, sorry. We have y minus y1 is equal to mx minus x1. Well, what are our x and y values? Well, for a given coordinate, that is exactly the x and y value that we need. So we can do y minus negative 1 is equal to negative 1 half x minus 1. And this negative 1 half can distribute to both parts, turns into a plus 1 half. This minus negative 1 turns into y plus 1, right? So now to solve, just to get y by itself, we need to subtract 1 from both sides. This turns into y is equal to negative 1 half x. 1 half minus 1 is negative 1 half. Now for the other coordinate, we have y minus 1 is equal to positive 1 half times x minus 1. And again, this 1 half distributes to both parts. So we have 1 half x minus 1 half. And then we add 1 to both sides. And this turns into y is equal to 1 half x. Negative 1 half plus 1 gives me plus 1 half. Very good. Nice. Now, technically, I've made a kind of a big mistake. It said x equals 4. I wrote the problem x equals 4, and I did x equals 1. Um, so, yeah, if you were thinking, why did he do x equals 1? Because he forgot the question that he just wrote down. So really, we would do all the same work, but instead, we would have y squared is equal to 4 that we're wanting to look at. So then this turns into y equals plus or minus the square root of 4, which square root of 4 is 2, so y is plus or minus 2. So now our two coordinates would be 1, comma 2, 1, comma negative 2, and now the m value here, 1 over 2 times 2, well, that's 1 over 4, m equals 1 over 2 times negative 2, so negative 1/4. Now I will say, I feel like I did something wrong with these two tangent lines. Um, oh, okay, no, never mind, I see it. So those look right. Okay, sorry. I take it back. Um, very good. So that is the basics for our implicit differentiation. Now, as always, a normal question to ask is something like find where there is a horizontal tangent line. I keep misspelling. It's almost like it's after midnight and I'm tired. Horizontal tangent line. And let's say our function is y squared plus x squared is equal to 25. Okay, so this turns out is the equation of a circle, but we don't really even need to know that um, for this. So we take this derivative and we remember y is a function, so we need the chain rule. This turns into 2 times y prime. X is not a function. Derivative of x squared with respect to x is just 2x. And derivative of 25 with respect to x is 0, right? It's just a constant. So now we want to solve for our y prime. So we're going to go ahead and do 2y prime is equal to negative 2x, and then divide both sides by 2y, so that y prime is negative 2x over 2y. Well, our 2's cancel. This is really just negative x over y. And perfect. So now we have this formula, this expression of our derivative in terms of our x and y value, right? Y prime is negative x over y. So horizontal tangent line means y prime has to be 0. So really, we want y prime to be 0, but we figured out y prime is negative x over y. So we really want to solve for all x and y values that give a derivative of 0, that give negative x over y to be 0. Well, the trick here is, well, okay, you can look at this a couple ways. So if you have this expression, 0 is equal to negative x over y, you have a couple of options. So first of all, if you're just trying to solve this bluntly, like for x, for instance, right, you can just multiply both sides, or you're trying to get rid of the fraction. If you multiply both sides by y, you say, okay, well this cancels with the y's on bottom, so this turns into just negative x, and then y times 0 is still just 0, right? And it turns out that's a pretty okay thing to do, because saying the fraction negative x over y is 0 can only happen whenever the top is 0 and the bottom happens to not be 0 as well. So as long as we just double check that our x and y values are valid, then, we're good to go. So really we have negative x is equal to 0. Well, that's just saying x is 0. So we just found what the x values must be. So we can plug that into the original function and say y squared is equal to, oh, sorry, y squared plus x squared is equal to 25. But if x is 0, then we have y squared plus 0 squared is 25. But we know 0 squared is 0, and adding a 0 does nothing. So you have y squared is equal to 25, and we figure out, we just do y is plus or minus the square root of 25, which we picked a nice number 25 for a reason, because this just turns into plus or minus 5. So the two coordinates, right, there's 2, because I know x has to be 0, and y can be plus or minus 5. So my two coordinates are 0, comma 5, positive 5, and 0, comma negative 5. Very good. Now, a slightly different way of tweaking the question is, what if I instead said vertical tangent lines? Well, again, I had that y prime is equal to negative x over y. Well, what makes us have a vertical tangent line, right? A vertical line, right, if this is the graph normally, then a vertical line would have to be a line like this, right? Well, this formula says y can be anything, but x has to be stuck at this value, maybe 2. So the equation of a vertical line is something like x equals 2, right? Y doesn't really change, or sorry, y goes everywhere while x doesn't change. So if we try to talk about rise over run, well, our rise is going to be something like, well, what's the change in y? Well, from negative infinity to infinity, I don't know, infinity, right? There's an infinite amount of rising here. And how much are you running? Well, 0. And dividing by 0 we can't really do, but it's supposedly dividing by something really small makes things huge. So it turns out that we get these vertical tangent lines whenever our derivative tries to divide by 0, right? So really the question turns into, instead of from before, where the tangent line had to equal 0, which really meant the top part of the fraction had to be 0, right? Now we need the bottom part of the fraction to equal 0. So this turns into, I need to solve for whenever the denominator y is equal to 0. Well, that immediately just gives us those values. Y is 0. Okay, great. So now again, plugging this into y squared plus x squared is equal to 25. Y is equal to 0 means you have 0 squared plus x squared is equal to 25, which turns into x squared is 25. And again, this gives us x is plus or minus 5. So our two coordinates happen when x is 5, y is 0, and when x is negative 5 and y is 0. And it turns out, if we look at the graph or we, consider a circle, right? Well, where is the tangent line horizontal? Well, it should be at the top and at the bottom, right? Well, where is the tangent line vertical? That should be on this end and at this end. Well, if my circle has a radius of like 5, like that equation that we just looked at, well then what are these coordinates? Well, this coordinate is going to be, well, we go to the right 5, up, down 0. This coordinate is we're going to the right 0, we're going to go down 5. This one is we're going to go to the left by 5 units, not up and down at all. And this one we go left to right 0, and then up 5. So our horizontal tangent lines were exactly those coordinates that we saw before, 0, comma 5, and 0, comma negative 5, and our vertical tangent lines are in fact at those reverse, right? X value is 5, y 0, x value 5, negative, sorry, x value of negative 5, y value 0. Okay, um, and if an exam says do this and it gives you the equation of a circle, you have to do the actual math. I know my circles so well. Here you go, right? We need to do the math here. We need to show the work. Um, so very good. That is implicit differentiation, which is actually just the chain rule, but used in a pretty unique context. Very good.